Now that we've actually seen how to find a Taylor series with a given center, what I'd like to spend some time on is looking at ways that we can actually put Taylor series to use. In this example, we're asked to use Taylor series to evaluate a limit, and that's the limit of 1 minus cosine of x divided by x squared. Note that this does give us an indeterminate form, and of course we could use L'Hopital's rule. But let's look at another way that we could approach this. In particular, what I want to use is the knowledge that cosine of x has Taylor series centered at 0, given by the sum from k equals 1 to infinity of negative 1 to the k times x to the 2k divided by 2k factorial. Now, notice that the reason I actually could choose to use this series centered at 0 is really coming from the fact that we really only care about what happens to this expression for values of x that are getting closer and closer to 0. What I'd like to do here is to write out several of the terms. This is going to look like 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. And in particular, now if I want to find the limit as x approaches 0 of 1 minus cosine of x divided by x squared, I can now think about replacing cosine of x with its Taylor series. So in parentheses, I'm going to replace cosine with 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. And everything else I'm leaving as it was in the original limit. So one thing to note is, first of all, I have 1 minus, and the very first thing I'm subtracting there is also 1. So we can cancel these ones. The other thing to consider is that there's still a minus sign out front that we need to distribute and multiply every term by a minus sign. What's going to happen here, in terms of what I'm taking the limit of, is that in the numerator we now have positive x squared over 2 factorial minus x to the 4th over 4 factorial plus what comes after. And again, we're dividing everything by x squared. And we know that if we divide everything by x squared, what we get is the numerator where every term has the exponent on x knocked down by 2. So this first term now becomes a constant, 1 over 2 factorial, or 1/2. And then we have minus x squared over 4 factorial, and so on. And this is now what we're taking the limit of. And I'll point out here that the ... part indicates that there are actually higher powers of x involved. So now I can focus on the fact that what I really want to look at is sending x towards 0. Any term that still has an x in it is going to go to 0 when I let x go to 0. And consequently, we're going to be left with the constant term, the only term that doesn't vanish, and that in this case is that 1/2. So that becomes the value of our limit. That's also what you should get if we were to apply L'Hopital's rule. And so maybe in this example, we can't really see what's nice about this because we have an alternative way to find this limit. But I'll point out that we can use this even a little bit more generally. Suppose that I don't know f of x, but in this case I know the Taylor series of f of x centered at 0. That's what I've given here, and we want to find the limit of this unknown function, minus 3x divided by x squared. I can really repeat the process of what I did above. So we're handed the Taylor series instead of us having to write it down. So if I write out the terms of this Taylor series, let's think about substituting those into the expression that we're trying to take the limit of. So right now I'm just writing exactly what we're given. However, when k is 0, in this instance we'll get a positive, we'll get an x times 3 squared. So we'll get 9x divided by 0 plus 3. And then the next term we'll get minus 27x squared over 4 plus 81x cubed over 5, and so on. So now the limit as x approaches infinity, not infinity, 0, is going to be let's see. So we want f of x. I'm going to replace that with what we just wrote out above. So this is the limit as x approaches 0 of 9/3 x, that's 3x, minus 27/4 x squared plus 81/5 x cubed, and so on. And we're subtracting 3x and dividing by x squared. Notice that right away I can note that the 3x's cancel. Here I don't have to distribute any negatives because we were just subtracting the single term from what we have in the parentheses. So I now have the question of what is the limit as x approaches 0 of negative 27/4 x squared plus 81/5 x cubed, and so on. And we're dividing that all by x squared. And in doing that, we're left with negative 27/4 plus 81/5 times x, and so on. And again, what's hiding in here are higher powers of x. As I send x to 0, anything that has an x attached to it will also go to 0, and we'll be left with the constant term. So what we're finding here is I can find limits involving this unknown function simply by knowing the Taylor series, as long as that Taylor series is centered about the value of interest, and in this case that's 0. So one of the ways we can use Taylor series, and likewise essentially Taylor polynomials, that's what I'm taking advantage of here, is to use them to find limits for functions related to the original function.